Hello. This week we began looking at the electric fields of distributed charges. We looked at their definitions and a general method for calculating the electric field of a distributed charge. We went on to look at both numeric and analytic approaches for determining the electric fields for uniformly charged rods, rings, plates, shells, and solid spheres. Nearly all the content this week was new to me, but from previous lectures and readings I was familiar with the concept of superposition used in the calculation of electric fields, as well as the formula for an electric field of a point charge, which was used at different stages in many of the calculations. Now we'll look at the content which was new. We can start by defining a distributed charge. A distributed charge is one which is spread throughout a space, either at many discrete locations or spread continuously. We can use this definition to create a general procedure used to calculate the electric field of a distributed charge. First, we must divide the charged object into pieces. We then find a mathematical expression for the electric field of one piece, and lastly, use superposition to sum the electric fields of all the pieces to make one net field. This is the general approach we'll take when deriving formulas for the objects we looked at next. The first object was a uniformly charged rod. In this case, we were trying to find the net electric field of the rod on the axis which perpendicularly bisects the rod. We first performed a numerical approach, where we separated the rod into a number of distinct sections, each with the same length. As the rod was uniformly charged, the charge on each of these sections will be equal, as charge density is proportional to length. This means we can treat each section as a point charge and superpose to get the net electric force. The fact that our observation location was on the perpendicular bisector plays an important role here. While the method would be the same if it weren't, in this case, the net electric field only operates in the direction of the bisecting line. Looking at the same problem analytically, we again separate the rod into n distinct sections with equal length. We then write out the formula for a point charge's electric field and substitute Q for a product of delta y, which is the height of one of the sections of rod. If we tend n to infinity, we can integrate from minus L over 2 to L over 2, rather than take the discrete sum, which gives us this formula for the electric field of a uniformly charged rod on its perpendicular bisector. Next, we looked at uniformly charged rings. The method used here was very similar to that of the charged rod. Our observation location was on the axis perpendicular to the plane the ring lies in, and passing through the centre of the ring. Much like the charged rod, in this particular case, the electric field can only operate in the direction of the perpendicular axis. Looking at the charged ring analytically, we again follow a similar process. We separate the ring into n distinct sections with an equal central angle, theta. This time, we write out the formula for a point charge's electric field and substitute Q for a product of delta theta. By tending n to infinity, we can integrate from 0 to 2 pi instead of discretely summing the point charges, and we are left with this formula for the net electric field of a charged ring when its observation location is on its perpendicular axis. The third object we looked at was a charged plate. This time, instead of point charges, distinct sections were charged rings, which we just obtained the formula for. To numerically find the net electric field, you sum the electric field of the charged rings. To analytically find the formula for the electric field of a charged plate with the observation location perpendicular to the plate and passing through the centre, we can divide the plate into n charged rings and write out the formula for the electric field of a charged ring and replace Q with a product of delta R, which is the radius of each ring. We can then integrate between 0 and capital R to obtain this formula. This object has two special cases. If the observation location is very far away, we can model the plate as a point charge, and if the observation location is very near, the electric field is a constant, as seen here. The last objects we looked at were uniformly charged spheres and shells. Looking at the shells numerically, we can separate them into n distinct charged rings and compute the net electric field by superposing them if our observation point is outside the shell. A property of these shells is that if the observation point is within the shell, the net electric field is 0. Analytically, we can model a uniformly charged shell as a point charge located at its centre when the observation is outside. If the observation point is inside, the net electric field is 0, as stated before. Looking now at a sphere, we can break it down into nested spherical shells. If the observation location is outside the sphere, it can be modelled as a point charge at its origin. If the observation location is within the sphere, you can ignore the shells with radius greater than the observation locations R, and you can model the remaining shells as a point charge with a charge proportional to the remaining volume. There was a lot of new content this week, but the part which gave me the most trouble was the observation location within a charged sphere. After reading the field of a charged sphere's physics book page, however, I feel I have a much better understanding. Thinking about these topics in the context of my major, computer science, I'm interested in finding out whether these shapes are considered when designing computer components, so that they don't erroneously interact with one another. This concludes my report on week 4's reading. Thank you for listening.